So, let us move on to another nature inspired optimization method. Before that, we look at this notion of what is are known as emergent systems, which basically say how complex behavior emerges from simple elements. We will see some examples here. This is often studied by people who study complex dynamical systems, and the idea is this, that collections of simple entities organize themselves. So, this is we are talking about self organization here themselves, and a large more complex entity emerges out of that. Essentially, the behavior of this complex system is a property that emerges from the interactions amongst its simple components essentially. So, an ant colony is like an organism that can, for example, find food very quickly, uh, but it is an ant colony which behaves like an organism, even though even every individual ant is a living creature inside that. The brain is made up of many billions of comparatively simple neurons, and it works as a larger organism. This thing, a flock of birds, for example, they move in synchrony. They tend to behave as if they are a larger organism essentially. Then the similar is true about termite mounds, or if you look at stock market behaviors, or formation of sand dunes for example, and many other things. For example, you can think of the corporate world also made up of complex organisms which are made up of simple elements coming together. So, hurricanes and cyclones also, we tend to think of them as one monolithic activity, but what is really happening is that the temperature is influencing individual molecules of the air to move around, and we can see a spiral in a cyclone and things like that essentially. So, quite some time ago, John Conway, he invented, as you can see in 1970, cellular automaton which he called as the game of life, and the cellular automaton is in principle an infinite array of this thing. So, you can think of it as a toroid closed array or something like that. Each cell obeys the following rules to decide its fate in the next time step. So, time moves in cycles. So, first time step, second time step and so on. So, in that sense it is like an automaton. It is a cellular automaton because there are a whole lot of cells which are being influenced by these rules essentially. So, for each cell the following rules apply. If the cell is alive, and that is in the first 3 rows, as you can see, you count how many neighbors are alive essentially. If less than 2 neighbors are alive, then that cell goes into a new state which is dead essentially. So, if you have less than 2 neighbors, then you die essentially. So, what do you mean by alive and dead? So, that it can be just states 1 and 0, for example. The explanation you can give, if you want to give an explanation, is that it was lonely or something like that. If a neighbor has 2 or 3 neighbors which are alive, then it stays alive. It is kind of stable essentially. If a cell has more than 3 neighbors which are alive, then it dies, and the explanation could be that it dies out of overcrowding essentially. So, these are the cases when you have an alive cell, but a dead cell also can come alive, and the situation is when it has exactly 3 neighbors which are alive, then the dead cell becomes alive essentially. So, you can imagine that you have this large or in principle infinite array, and in which certain things are. So, for example, if this cell is alive, and if this cell is alive, and if this cell is alive, then that central cell has 2 neighbors which are alive. So, it will continue to be alive and so on and so forth, and you can imagine this. So, it turns out that this very set of simple rules gives rise to very stable and persistent patterns in this world, which Conway called as the game of life essentially. So, the simplest is for me to show you something which you can find on the web. if you just search for Gosper's glider gun, you can see that there is a cellular automata, and there is an illusion of movement which is happening. So, if you work out the details, for example, you will see that if you start off with this combination, you will move to this one in the next time step, then to this one in the next time step, this one in the next time step, and this one in the next time step, and after these 4 time steps, you have come back to the same shape, but in a different location essentially. So, there is this illusion of some creatures which are moving in space. So, this part here is the gun which is shooting these creatures out into space, which seem to be traversing space actually. Though in practice what is happening is that every cell, this whole thing is some cellular automata. Every cell is following the rules that we have just described, and when we show black basically shows that they are alive, and white shows that they are dead essentially. So, cells keep growing and dying, coming alive and dying or remaining stable, but it gives us the impression that there is some emergent creature, for example, which is traversing down the stream. You can also see that if there is a square of 4 neighboring cells, then because of the rule that each of them has 2 or 3 neighbors which are alive, it is a stable set essentially. There are other uh, combinations. So, for example, if there are 3 cells and they are alive essentially and surrounded by dead cells essentially. So, you can see that a cell here and a cell here will become alive in the next cycle, because it has 3 neighbors which are alive, whereas this cell will die and this cell will die. So, you should work out this detail and see that that is the case. So, this looks like a spinning structure if you were to implement it yourself and see, because in every cycle from there you will go to this cell, because those circled cells have become alive and those other 2, this cell has died, this cell has died, and the other 2 cells have become alive. In the next cycle, it will again rotate by 90 degrees and so on. So, there are very interesting patterns which the game of life shows us, and it can be quite fascinating to work with them. But the idea is that simple rules give rise to can give rise to complex behavior. The same idea is followed in the world of chaos and in fractals. So, a fractal is a never ending pattern. Fractals are infinitely complex patterns that are self similar across different scales essentially. We will see what we mean by this. They are created by repeating a simple process over and over in an ongoing feedback loop essentially. Driven by recursion, fractals are images of dynamic systems, which some people say the pictures of chaos. Fractal patterns are extremely familiar since nature is full of fractals. So, for example, trees have a fractal structure, rivers have a fractal structure, coastlines have a fractal structure. So, if you take images of coastlines and you keep zooming in, you will see that the images will look similar essentially. So, that is the idea of fractals in general. So, here is this something called the Sierpinski triangle, and you can see that the more we zoom in, the more it looks the same essentially. That at these are infinitely recursive patterns which are repeated essentially, and that is known as the Sierpinski triangle. So, you can see on the left hand side, for example, how you are creating these recursive structures essentially. So, essentially a straight line like this is converted into a structure like this. Then that happens at different levels. So, here it is happened at a different level and so on, and so you keep going inside and you keep getting these structures which is like a fractal structure. On the right hand side also you can see that this pattern here is repeated here at a lower level, and you keep doing that at still lower levels, and you will get patterns which look self similar at different levels of detail essentially. So, let us talk a bit about the human brain, as some people have called it the most complex object in the known universe. The brain is the most complex organ in the human body. It produces our every thought, action, memory, feeling and experience of the world. This jelly-like mass of tissue weighing about 1.4 kilograms contains a staggering 100 billion nerve cells or neurons. The complexity of connectivity between these cells is also mind-boggling. Each neuron can make contact with thousands or even tens of thousands of other neurons. So, this I have taken from this article I was reading on New Scientist. This thing. Our brains form a million new connections for every second of our lives, and the pattern and the strength of these connections is constantly changing, and no two brains are alive essentially. So, this is just for the sake of completeness diagram of a biological neuron. So, this is basically the neuron here. It has a cell body which is called the soma, and then it has these dendrites coming out, and the signal is going out into another neuron essentially. So, they between a combination of chemical and electrical signals, the synapse for example, a neuron sends signal to other neurons essentially. So, a biological neuron from the brain receives several inputs via its dendrites. So, these are all the inputs that it is getting, and it has some built-in threshold like function which says that after the inputs reach a certain threshold, it generates its own output in turn, which is distributed to other neurons in the brain. That is how signals travel in the brain. The axon branches out. So, this is the main output of a neuron is called the axon, and connects to dendrites of other neurons via synapses, which transmit the signal chemically to the other neurons essentially. The shaded portion of the neuron is the nucleus of the cell essentially. So, we each have something approaching 100 billion nerve cells or neurons in the human brain. This is from another article that I was reading, which is more than the number of stars in the Milky Way. Each of them can be connected directly with maybe 10,000 others, totaling some 100 trillion nerve connections. If each neuron of a single human brain were laid end to end, they would be wrapped around the earth twice over essentially. So, that is one single human brain. Computationally, we model neurons as simple devices, and they are tied up to emergent systems in that sense that interaction between simple devices give rise to complex behavior. We had mentioned neural networks a little bit in the beginning. So, here is a kind of a repetition of that. So, this is a feed forward artificial neural network. It encapsulates a function where the output is a function of the input essentially. So, there is an input layer and there is an output layer, and there is some hidden layers, and nowadays of course, we have in deep neural networks we have many hidden layers essentially. The artificial neural network, as it is called ANN, learns the function through a process of training when a large number of labeled patterns are shown as input, and the ANN generates an output. Then the algorithm known as backpropagation or backprop, it propagates the error back to tune the weights of the connections, and that is how neural networks work essentially. Now, people have used neural networks in artificial life. So, in particular, this scientist called Carl Sims, he worked on artificial life and evolved creatures and so on, and essentially he was following something like a genetic algorithm essentially. So, his life forms had very unique kind of shapes. Two of them are shown here, but they had a neural internal system. So, these are different kind of evolved creatures that he shows in his publication. So, I have taken this from one of his papers. Each of them is like a living creature, and each of them is been evolved for locomotion. So, he wanted to show how different forms of locomotion are possible. I do not have a video, but I can give you a link to some of these videos where you can see these creatures moving around. Different designs evolved for walking creatures, and this figure is from his paper in 1994. But there is also a very interesting documentary called The Secret Life of Chaos. which I will strongly recommend that you watch. It's about 1 hour long, and you can find it on various places in the net. It starts off by work of Turing, and then eventually goes into things like chaos and how complexity can emerge out of simplicity. And it illustrates this idea of emergent systems very well. So, having looked at this notion of emergent systems, let's take some inspiration from ants and how they cooperate to form a cohesive social structure. So, we had mentioned the science of semiotics. Biosemiotics is the study of signs and symbols and their use or interpretation. This thing from the word Greek word, which stands for interpret as a sign, essentially. So it's a field of semiotics and biology that studies the pre-linguistic meaning making as to how symbols, which are chemical symbols and physical symbols, can be interpreted as meaning by other life forms. So that's why the word biosemiotics. So, and animals frequently mark their territory. For example, you must have seen dogs do it, but we are interested in ants at the moment, and we are in particular interested in ant colonies. And the idea is that ants live in a complex social colonies, with the queen being the leader and the workers foraging for food and protecting their home. Essentially. So every ant colony has a very well defined hierarchical structure. The term ant colony describes not only the physical structure in which the ants live, but also the social rules by which ants organize themselves, essentially, and the work they do. So basically, they work in a very cooperative fashion. Some workers become foragers, they go out looking for food when they mature, and then they leave the nest in search for food and they bring back the food. And that's how the ant colony grows, essentially. This cooperation and division of labor, combined with their well developed communication systems, which is what we want to look at, has allowed ants to utilize their environment in ways approached by few other animals. So, here is a small illustration of what ants do. They are looking for food, essentially. So, let us say that 5 ants A, B, C, D, and E go out in search of food. So when they come out of the ant colony or ant nest, they go off in some random directions in search of food. And here I have shown 5 ants which are going off in search of food, essentially. The thing about ants is that each ant lays a trail of pheromone wherever it goes. So these lines that you see on the screen are like trails of pheromone. And essentially, ants have a simple rule that when they have to go somewhere, if they sense pheromone somewhere, they just follow the path, essentially. So one ant follows the other. So more ants that emerge will tend to follow some pheromone trail, essentially. So initially, let's say there are these 5 ants and they have all gone in search of food. We will see that ant A finds some food. What does it do? If it finds some food, let's say there was some lump of sugar or something here, it picks up the food and starts back to its nest. How does it go back? It simply follows the pheromone trail that it itself has created. Meanwhile, if other ants like F, G, and H have emerged, they will also follow some trail or the other that you can see. The pheromone trail is what guides all ants, essentially. So they lay pheromone wherever they go, and they follow pheromone whenever they have to go somewhere. So eventually, what happens is that as more ants travel on the trail, they deposit more pheromone, and the trail becomes stronger and stronger, eventually becoming the caravan that you might see raiding your food. So you must have seen that ants always travel in caravans, and they are always ferrying food from one location to another, and this is how it ends up looking, essentially. After some time, all the other trails are abandoned, and all ants now follow the trail. For example, that ant A had found some food there, Now all the ants are going there and ferrying foods from there. All this happens by means of following pheromone trails, which is an example of biosemiotics that we were talking about. What is interesting that people have studied is that they tend to find the shortest path essentially. So if you put in an obstacle on the path, let's say all these ants were going from left to right to start with, and suddenly you have placed an obstacle, then obviously they will just start searching again in some sense. And eventually it turns out that because the shorter path takes less time, so more pheromone is laid on that. So eventually the new path will be the shorter path that they will find. And we want to capitalize upon this behavior to develop this, look at this algorithm called ant colony optimization. And it's a method that takes inspiration by the semiotic communication between ants. Each ant constructs a solution, whatever problem that we are trying to solve, using a stochastic greedy method. What is a stochastic greedy method? Basically, try to follow the pheromone trail to a large extent, probabilistically, using a combination of a heuristic function and pheromone trail for following. So, since we are solving a particular problem, we will use a combination of both of these and construct these solutions. This is related to a class of algorithms also known as swarm optimization, how swarms of simple creatures behave in a emergent fashion. It's easily applicable to problems that can be reduced to graph search. It was presented by Dorigo in 1992, and like he did, we will illustrate this algorithm with the example of the traveling salesman problem. So this is the problem for the traveling salesman using the ant colony optimization, ACO as it is known. So initially, of course, we don't have a best tour. How do we do this? Now we randomly place m ants on n cities that we want to travel. Each ant constructs a tour in a greedy stochastic manner. We will describe this shortly. And we always keep track of the best tour that some ant has found. And each ant deposits pheromone only on the tour that it has traveled on, essentially. So ants construct tours, they travel from city to city, and they keep laying pheromone on those tours that they have constructed. How much pheromone they deposit is something which Dorigo tells us. We will look at that in a moment. And we keep repeating that until some termination criteria. This is a little bit more detail. First, as before, we say randomly place n ants on n cities, and for each ant A, you construct a tour of n cities. Remember that there are n cities that they have to travel, and at every point, it selects an edge from the distribution which we will see based on a probability for that particular edge. And after it has constructed the tour, we of course keep track of the best tour. That's always the case for us. And then we look at the how to update the pheromone. So for each edge UV in the ants tour, we deposit pheromone which is inversely proportional to the cost of the tour found by the ant. So inversely proportional or proportional to 1 by tour length. So which means that ants which find shorter tours will deposit more pheromone, and ants which find longer tours will deposit less pheromone. So from let's look at how this greedy tour is constructed. So let's say we are talking about the kth ant, and it is going from city I to city J. Essentially, will it move from city I to city J? We said that we'll do this in a greedy stochastic fashion, and we do it with a probability which is given as follows. So the probability is the probability of kth ant moving from city I to city J at some point t. It's governed by two factors. One is the amount of pheromone on the edge. So tau ij is the amount of pheromone on edge ij. How much pheromone that edge has. So remember that the ant has to choose between some number of edges or some number of cities that it can go to, and it looks at how much pheromone each of those edges has. That's one thing it looks at. The other thing it looks at is called eta ij, which is the visibility, which is inversely proportional to the distance between cities I and j. So it has two tendencies. One is that it tends to go to the city which is closest. So that's like the greedy search algorithm that we had started off TSP with. Just go to the nearest neighbor. But it has another tendency that follow that edge which has more pheromone on it essentially. And it looks at a combination of both of these edges. We have used the term allowed cities because we don't want premature cycles to be formed essentially. So of all the edges that it can consider, it tries out all of them. So for all neighbors which are allowed, it computes this and then it picks the node edge with the neighbor with the highest probability, and it moves to that. So it can move to any one of the neighbors, but it will move to one of them with a probability which is proportional to this product of the amount of pheromone and visibility, which is how close it is essentially. So exactly like what we did earlier, uh, which move to make is chosen probabilistically. So if there is pheromone on that edge, it's likely to move. Otherwise, it's not likely to move. So it basically does a greedy tour construction, except that it is not deterministic greedy, it is stochastic greedy, and the probability of moving from city I to city J is given by these two factors. How does it update the pheromone? That's the second question that we have to address. So after constructing a tour in n time steps, remember there are n cities, and in n time steps it moves from one city to the next city. Each ant k deposits an amount of pheromone which is given by a constant q divided by the length of the tour found by the kth ant. So Lk stands for the length of the tour found by the kth ant on the edges that it has traversed. So it deposits the same amount of pheromone on every edge that it has traveled, and the amount is dependent on what is the size of the tour it has found. So it is inversely proportional to the cost of the tour Lk, which is found by that ant. And Q is some appropriate constant that we will use. So if there are m ants, remember that there were m ants to start with, and we place them on some random cities, and then they constructed the tours and so on. Then we sum up the tour, the pheromone on every edge by computing this for every ant that has traversed that edge essentially. So remember that not every ant will traverse every edge essentially, but for whichever edge, whichever ants have traversed over it, depending on the length of the tour they found, they will deposit some amount of pheromone, and that is the delta tau ij that we have computed. There is another feature that we follow from nature is that we update. So remember that there are n cities and it takes n time steps to construct a tour. So we look at the pheromone at time t, tau ij. We say that some of it evaporates over the period of time. So we have this rate of evaporation called rho. So only 1 minus rho of that remains. But this new pheromone that is added to the those edges at the end of the tour construction cycle, which is t plus n time essentially. So in that manner, uh, every ant deposits pheromone on every edge that it has traversed, and this happens at the end of n time steps when it has constructed the tour, and then the next cycle begins as before. So with that, we come to an end with this last randomized approach for optimization that we saw. And next we will move on to the well-known algorithm called A star, which is used for finding optimal paths in graph search.